In this lesson, we're going to talk about the binomial theorem. So you may recall that we already know how to expand the binomial square. A plus b squared is a squared plus 2ab plus b squared. And then some of you may also know how to do the binomial cube. A plus b cubed becomes a cubed plus 3a squared b plus 3ab squared plus b cubed. What we're interested in doing is expand this even further, go beyond 2 and 3 into higher and higher integers. So we want to find a formula for a plus b to the n. That way, when we have whatever n positive integer we need, we can then expand out the binomial raised to that power of n. And that's what the binomial theorem is going to do. So I'm not going to derive it for the power of n, but I'm going to do it by an example with the power of 7. So I'm going to expand a plus b raised to the power of 7. Now, if we go by first principles, when we say a plus b raised to the power of 7, we just mean multiply a plus b times itself 7 times. So that's the first principles version of a plus b raised to the power of 7. Now, as we actually multiply this out using the distributive property, what we are doing is we are, in each individual calculation, we are taking one term from each of the parentheses and multiplying them all together. So we will have a total of 7 terms, depending on which one we pick, that multiply together each time we do a multiplication problem. So as an example, if we had chosen to pick the a from the first set of parentheses and the a from the second, and then the b from the third, and then again the a from the fourth and the a from the fifth, and then the b from the sixth and the b from the seventh, this would be one of those distributive property calculations we would have to do, and of course there's a whole lot of these. But each of those, of course, uses exactly one of the a or b from each set of parentheses. So we have a total of 1, 2, 3, 4, 5, 6, 7 terms getting multiplied together in the end. So in this particular example, we ended up getting a times a times b times a times a times b times b, which when simplified, because it's all now one big term, becomes a to the fourth and b to the third. So here's a to the fourth, b to the third. Now, this is one of the multiple distributive property terms we would have to find. But there are lots of others that would also have exactly 4 a's and 3 b's in just a different order. So there are other terms that could be like terms with this a to the fourth b cubed just by picking the a's and b's in a different order. Now that's the key. If we're picking them in a different order, it's just rearrangements of these letters, just like you rearrange the letters in a quote-unquote word. So how many different rearrangements of 4 a's and 3 b's could we get to get all of the like terms that will end up giving me a to the fourth b cubed? Well, if we're rearranging the 7 letters, 4 a's and 3 b's, we would have 7 factorial for all the arrangements and then divide by the 4 factorial and by the 3 factorial to take into account the repeat letters of the a's and the b's. Well, you might recognize this as a combination. Either you can interpret it as 7 choose 4, or you can interpret it as 7 choose 3. So really, the number of arrangements that give you a to the fourth b cubed from this binomial expansion is 7 choose 4 or 7 choose 3. So that becomes the coefficient of the a to the fourth b cubed term. Now, of course, this is not the only term in the expansion. There are going to be a whole bunch of other terms. However, in each term that we look at, we're going to be taking exactly one of the a or b from each set of parentheses. So since there are 7 parentheses, there's going to be a total of 7 of these when we are done for each different type of term. So for example, a to the fifth has to go with b squared, or a to the first has to go with b to the sixth. That way, when we're done, we have a total of 7. So that allows us to then generalize how we can get the coefficients for any individual term, which I'm going to summarize on the next page. So when we are expanding a plus b to the n, and we're dealing with n is going to be a positive integer here, you're going to have, for example, n choose 0, where you have all a's, n of them being a's, and then 0 b's. So that means that you're picking the a from every single set of parentheses. Or you could have n choose 1, and then you have one of the b's and n minus 1 of the a's, one less than the total. And then n choose 2, and you have n minus 2 of the a's, so 2 less than total, and that leaves you with b squared, and so on until you get n choose n, and there's 0 a's, and then all of them are b's. So that's how you can find the different terms of the expansion of a plus b to the n. So this formula here is called the binomial theorem. Now the theorem does look a little intimidating, but it's actually a relatively straightforward concept, although some of the problems might get complicated. So we're going to do an example where we expand out a plus b to the fourth, and I'm going to show you how to utilize that theorem. So in order to expand a plus b to the fourth, well, we have to start by finding the coefficient for a to the fourth. Well, we have all of them being a. So that would be 4 choose 0, and then we went to a to the fourth. And then we'd have b to the 0. I'll go put it in anyway. Then we're going to go to the next one that has 1 fewer a, so a cubed, and then b to the first. So it's going to be 4 choose 1, and then a cubed, b to the first. And then we're going to take 1 fewer a, so now we're going to only have 2 a's, and then that means b squared as well. So that's 4 choose 2, a squared, b squared. And then we're going to go one further, so 4 choose 3, a to the first, b cubed. And then finally we're going to have 4 choose 4, and then we're going to have absolutely no a's, so a to the 0, and all of them will be b, so b to the fourth. Now, using 4 choose 0, 4 choose 1, etc. in this order, I did it so that the subscript there increases from 0 up to 4, but you could go just the other way. So 4 choose 0, remember, is exactly the same as 4 choose 4. So you could have done 4 choose 4, and that matches up with how many a's you have. This one is going to be matching up with how many b's you have. But again, either way is okay. So now we're calculating each of these coefficients. So we'll start with 4 choose 0. So of course 4 choose 0 is 4 factorial divided by 0 factorial times whatever's left over, which is another 4 factorial. And remember, 0 factorial is just 1, so everything cancels and you basically get 1. So now let's look at 4 choose 1, which is going to be 4 factorial divided by 1 factorial, and what's left over with 3 factorial. And again, I can split the 4 factorial into 4 times the 3 factorial, and the denominator, 1 factorial is just 1. So now you notice that the 3 factorials will cancel, and so we end up with 4. So now let's figure out what 4 choose 2 is going to be. So again, 4 choose 2 will be 4 factorial divided by 2 factorial, and then the other 2 factorial. And so again, I can split the 4 factorial into 4 times 3 times a 2 factorial, and then the denominator 2 factorial. This one I'll just say 2 times 1, and then I'll leave this other 2 factorial alone. So we end up with 4 times 3 divided by 2 times 1, which simplifies to 6. Now 4 choose 3 is exactly like 4 choose 1 because it's 4 factorial divided by 3 factorial, 1 factorial, so that's going to equal 4. And then 4 choose 4 is going to be exactly like 4 choose 0, so that's also going to equal 1. And so we can finally write out the simplified version of this expansion. 4 choose 0 is 1, so don't bother writing the 1. B to the 0 is also 1. Again, don't bother writing it. So I have a to the fourth. And then for a cubed b, again, I'm not going to bother writing that extra 1. 6a squared b squared, and then plus 4ab cubed. Again, I'm not going to bother writing that 1. And then b to the fourth. Again, there's a couple of 1s I'm going to ignore. And that is the expansion of a plus b raised to the power of 4. So now for these examples, I'm going to do the combination calculation, n choose r, whatever, on the calculator rather than doing it manually. So the first example here, we want to find the x to the fifth term in the expansion of x minus 4 raised to the 8th. So the first thing I notice is that because I'm raising to the 8th and I want x to the 5th, and there's the x, I'm going to have to take 5 of those x's, but then there's still 3 left over parentheses that I have not taken into account. So I'm going to have to take 3 of the negative 4. So x to the 5th and then negative 4 to the 3rd. But I've ignored the coefficient here. So the coefficient, of course, is going to be 8 choose 3, or for that matter, 8 choose 5 would work just as well. So we're going to use the calculator to calculate 8 choose 3. So first we hit the button 8, the number 8. Then we find the math button. And then we scroll over to the right to get probability. And then we scroll down to the 3 nCr. And then you hit enter on that. So once you've done that on the blank screen, your calculator should say 8C, and then there should be a blank, assuming you're using the new operating system. So it's the 8CR. In this case, we want to plug in either 3 or 5 over here. So in this example, I chose to do 8C3. So 8C, and then that's where I enter my 3. And then again, we hit the enter button. And the calculator gave me the number 56. So the 8c3 value is 56. I also have to do x to the fifth, and then I need to do a negative 4 cubed, which gives me negative 64, and then I can simplify by multiplying 56 by negative 64. And that gives me negative 3584. And so the x to the fifth term in this expansion is negative 3584 x to the fifth. So let's do the next example. This time we want the x squared term, the expansion of this. So of course I'm going to have to square the 2x so I can get my x squared, but of course I'm going to have more than just the x squared. It'll be 2x being squared. And I also have to raise plus 5 to the power of 4 so that altogether I've used 6 parentheses. Two of them I took 2x out, and then the others I took the plus 5. So this is what I need, but I still haven't written the coefficient. So for variety, I'm this time going to call it 6c2. It could just as easily have been 6c4 because I could either take these two or those 4 into account over there. So this is the binomial coefficient, and then I got to work out what everything else is. Now using the nCr button on the calculator again, I did 6c2 and I got 15, and then when I square the 2x I get 4 by squaring the 2, and then x squared, and then when I raise 5 to the power of 4 I get 625. And then finally, 15 times 4 times 625 is 37500. So the term is 37500 x squared. Now this one's a little more complicated. In this case, we have x's in both terms of the expansion. So when we want x to the sixth, it's not so obvious what term is going to get me x to the sixth. So we have to be a little more careful. So we've got this binomial, still 2 terms here, but one's a fraction and one got x squared in it. We're raising it to the power of 12. We want the coefficient of x to the sixth. So here's what's going to happen. We're going to have r number of x squareds. I don't know how many that's going to be yet. We're going to have some number of x squared. Let's call it r. And then whatever is left over, the plus 4 over x, has to have all the remaining ones. So if there are a total of 12 and we used r of them for x squared, then 12 minus r is what's left over, and that's how many of the plus 4 over x's we're going to have. And then the coefficient is going to be 12 choose r, because it's 12 from here, and then r because we need r of them from there. We'll worry about this later. We're going to focus primarily on this temporarily. So what I'm going to do temporarily is ignore any coefficient stuff. So I'm going to ignore the 12CR entirely. And I'm also going to ignore this positive 4. And I'm going to focus only on how many x's I need. So I have x squared raised to the r. And then, yes, it's 4 over x, but I don't care. It's just something over x to the 12 minus r. Well, that means I'm going to have x to the 2r and then x to the 12 minus r in the denominator. And I can subtract the exponents very carefully to get how many of the x's total I will have. So I will have x to the 2r minus 12 minus r. And again, when I combine like terms, I distribute the minus sign first. So I'm going to have 2r minus negative r. So it's 2r plus r, which is 3r. And then minus 12. So it's really x to the 3r minus 12. Now remember, I want x to the sixth. So I want x to the 3r minus 12 to match up with x to the sixth. Well, that means that 3r minus 12 must equal 6. And once we know that 3r minus 12 is equal to 6, we can figure out what the value of r needs to be. And so we solve and we end up with r must equal 6. So now we know we have to have exactly 6 of the x squareds, and then 12 minus 6, which is another 6, of the 4 over x's. And this is going to have to be 12 choose 6. So now we're going back and trying to take into account all of those coefficients. So we're not just focusing on x. We've figured out exactly how many x's we need. So we now need to work out what the coefficients are. So we have 12 choose 6, and then x squared raised to the 6th, then 4 over x also raised to the 6th. Now because I got a fraction here, I'm going to make fractions out of these things so that they can be multiplied easily. So 12 choose 6 is 924, so I'm going to call it 924 over 1. X squared raised to the 6 is x to the 12, so I'm going to call it x to the 12th over 1. And then 4 to the 6th is 4096, and then x to the 6th is going to be x to the 6th. And so really I got to multiply all the numerators and then all the denominators, and then of course cancel the x's. So when I multiply the 924 times the 4096, I get 3,784,704, and then x to the 12th over x to the 6th gives me x to the 6th, technically divided divided by 1, but I don't really need that. However, reading the question carefully, it just wanted the coefficient of x to the 6th. So this is not the answer. The answer is just the number in front. So the coefficient of x to the 6th is going to be 3,784,704. And that's the end of part A. Now part B wants us to find the constant term. Well, the constant term is the one that has no x's in it. So I have to do something similar to what I did over here and try to get no x's, or in other words, x to the 0. So again, I know that I need to have 12 choose something, so 12 choose, let's say, r, and then I'm going to have r of those x squared, and then I'm going to have all the rest of the things, so 12 minus r, of the 4 minus x's. So how many of our x squareds I have to take exactly all the remaining ones have to be 4 over x's. So this is my setup, and again, I'm going to ignore the coefficients, the 4 and the 12, choose r, and focus only on the x's temporarily. So I get this again, x squared raised to the r, and then 1 over x raised to the 12 minus r. And again, I made a fraction out of that one. So again, I simplify. So I have x at 2r in the numerator, x at 12 minus r in the denominator. I subtract the exponents top minus bottom, and of course, don't forget the parentheses for the denominator. So 2r minus negative r becomes 3r. So I have x to the 3r minus 12. Now, this does match with this because it's the same problem that we started with. So the unknown coefficient will always be this with this process. What's different though is that this time I want this to be x to the 0, not x to the 6th. And again, the reason I want that is because I want the constant term. The constant term has no x in it. X is a variable. When the variable disappears, what you're left with is a constant. So this is really what I want to happen. So when I realize that 3r minus 12 must equal 0, I can solve and I can get r equals 4. And that's now the r I'm going to use back in the original where I actually took the coefficients into account. So I'm going to have 12 choose 4, because that's 12 choose r, and then I'm going to have x squared to the 4th, x squared to the r, and then 4 over x to the whatever's left over. So when I do 12 minus 4, I get 8. So 4 over x has to be raised to the 8. So again, 12 choose 4 became 495. I made a fraction out of it. X squared to the 4th became x to the 8th. I made a fraction out of it. And then I raise 4 to the 8th. I get this number. And then, of course, x to the 8th, and I get that. Now, of course, the x to the 8ths are going to cancel, which is what I wanted. I wanted a constant, so no x's left over. And so all I got to do now is multiply these two together to get my final answer. And again, with the x's disappeared, it becomes 32,440,320. Now, I don't have to worry about coefficient of x to 6 or whatever because it's already just a constant. There can't be a second version of this answer. So either way, I set up the unknown term with an r in it, and then worked out what r needed to be to get the thing I wanted. In the first case, x is 6. In the second case, x is 0. And then I went back and I figured out what it was going to be in terms of r. When I was doing the check, I ignored coefficients temporarily, just focused on x, and then I went back and actually worked out what the coefficients were. And that's the end of the lesson.